Yes. Sure.
So, hello everyone. Welcome to the Bangalore Theory Seminars. With us today we have Rohit Vaish. Rohit is an assistant professor in the Department of Computer Science and Engineering at IIT Delhi and an associate faculty at Yardley School of Artificial Intelligence. His research interests lie in the area of computational social choice, and his works lie in the interface of economics and computer science, especially in fair resource allocation and fair matching.
Thank you, Manisha. Thank you, Siddharth, for the invitation. And thank you all for coming here. It's a homecoming of sorts for me because I spent a few years here for my PhD, and it was a great time. So great to be back. Today I'll talk about best of both worlds in fair division. Very broadly speaking, this work is going to address a problem in the area of fair division, which talks about distributing resources fairly among people based on their preferences. And what I'll talk about is a combination of two very computer sciencey approaches, randomization and approximation, how they can sort of very meaningfully come together to help us out with an economics problem, that of allocating resources. Okay, so I hope you'll appreciate all these elements as we go along. Before I get into the talk, I just want to do a very quick introduction about myself, because I'm not sure if I've met everyone in the crowd before. So, like Manisha said, I work at the computer science department at IIT Delhi. After finishing my PhD from here, I did a couple of postdocs. I spent some time in the US at RPI and then a little bit of time at TIFR. And my research interests are broadly in the area of economics and computation, problems at the interface of computer science and economics. And specifically, I work in the area of computational social choice. So social choice is a subfield of economics, which talks about making collective decisions, right, based on people's preferences. So decisions that affect the society as a whole. And my goal is to understand what is the role of computation in such collective decision-making problems. Just to give a very, very brief sort of overview of some of my research is basically divided into these three sections: voting, matching, and fair resource allocation or fair division. In the voting problem, typically you are given the preferences of voters or agents, and you want to select some kind of winning candidate or a winning committee for the society. In this space, I have thought about the problem of manipulation, how people can strategically manipulate the voting rules, okay, in their selfish favor, and how can computer science or computation serve as a barrier against this kind of strategic behavior. I've also looked at problems in proxy voting, where instead of voting directly, you sort of delegate your vote to a trusted person or some expert, and so on. In the matching world, one is typically thinking about, let's say, two sets of agents, say job applicants in jobs or students in schools, etc. And you have to match these agents with each other, taking into account their preferences. These are known as two-sided matching problems. In this case, I have looked at something called the stable matching problem of the Gale and Shapley stable matching model, and specifically on problems related to manipulation or strategic behavior in stable matching problems. I've also got a little bit about sort of generalizations of stability concepts in the context of fractional matchings.
What is fractional?
So you're looking at a fractional matching, meaning instead of being completely matched with one person, you can sort of 10% of the time spend time with them and 20% of time with someone else, and so on. In this case, how do you define the idea of a blocking pair? Right? So turns out there is more than one way to define what stability means in this setting, and some of them are computationally nice, some are not. So sort of for today, my focus would be in this third section in the fair division part, and I'll talk about. So broadly here, I've thought about the problem of finding fair and economically efficient allocations, mostly for resources which are indivisible or discrete. Okay, and the problem that I'll describe today sort of fits into this research agenda. Okay. But if you are interested in any of these other topics, I'm very happy to talk to you after this talk. All right. So I'm going to talk about a work called Best of Both Worlds, Ex-ante and Ex-post Fairness and Resource Allocation. This is joint with Haris Aziz, Rupert Freeman, and Nisar Shah, and it appears in the Operations Research Journal. Okay, so the problem that I'm going to talk about, it deals with indivisible or discrete resources. And these kind of resources, they arise in a variety of applications. Okay? For example, say you are thinking of dividing an inheritance among a bunch of siblings. Okay? Now, this inheritance or inherited property could consist of various kinds of objects. Let's say a house, or say a car, a very valuable painting, a very valuable ring, and so on. And very often these objects are discrete in nature. You cannot sort of break them fractionally and give it to different agents. For example, if you have a car, you don't want to divide it into three parts and give it to three different people. It will lose all of its value. So every resource must go to entirely to one person or the other. You cannot fractionally divide resources. But you still need to divide these resources fairly among the people based on their preferences. Okay? Someone might be more interested in the house, someone maybe in the car, and so on. And you want to sort of take those interests into account. Okay? So what is fair depends on what people's preferences are. Okay? It's not just enough to give everyone the same number of items. You also have to take their interests into account. Likewise, let's say you are, IISc, you have to figure out which students get to do which courses. Now, a seat in a course is a discrete resource. It can only go to one student or another. You don't want one student to attend the first 2 months and the other to attend the last 2 months. That's not how you allocate seats in courses, right? And you still want to be fair to the students, right? You don't want to give the best courses to the PhD students and deprive the master students, or you don't want CS students to have all the fun. You should also want the maths students to be able to take some of the star courses. So you have to be fair to different sort of demographic groups among the students. And also, say you are thinking about allocating medical resources, say like COVID vaccines or PPE kits. Right? Again, you have to be fair in distribution of those resources, right? You work across age groups, across regions, across professions, and so on. So these are all examples, and surely there are many, many more, where you are dividing a bunch of discrete resources, and you have some fairness desiderata when you want to divide. Okay. So I want to sort of give you a very, very simple model to think about some of these questions. In this model, we have a bunch of agents given by these happy triangles, and a bunch of discrete or indivisible goods given by these circled objects, A, B, C, D, and E. Now, every agent has some value for getting a good, some happiness, units of happiness that it derives if it is given that good. For example, let's look at this blue agent. It gets 5 units of happiness if it gets the good C, 1 unit of happiness if it gets D, and B is worthless for this blue agent. Okay, so the bigger this number, the happier you are to get that item. Okay. So you're given this data about people's preferences. Now, what we are seeking, what we're looking for, is an allocation, which is just a way of assigning every good to exactly one person. For example, in this picture, I've given good A or item A to the red agent. The blue agent gets B, D, and E, and green gets C. Sorry, the colors are a bit off, but I hope you can understand what's going on. So we are looking to find allocation subject to some nice properties, which I'll describe in a second. But this is the object that we are trying to find. Now, one assumption that I'll make throughout this talk is called the additivity assumption on the valuations or the preferences of the agents, which is to say that if you get a bundle of items, let's say blue is getting B, D, and E, the union of B, D, and E, its value for that bundle is the sum of its values for the individual items in that bundle. Okay. In other words, blue's preferences are adding across the individual items in a set. They're additive. So this is a simplifying assumption. It may sound strong, right? Sometimes preferences are not additive. For example, if I give you the left shoe, it's worthless. But if I just give you the right shoe, it's worthless. What really matters to you is the two things together. Sometimes preferences can be non-additive, but for the purpose of this talk, I'll look at only additive valuations. I'll come to non-additive preferences towards the end of the talk. But it's not so bad to assume additive preferences because if you have to express people's preferences, in general, you would like to express the preferences over all subsets of items, right? So if there are, say, k items, there are 2 to the k subsets that you're working with. that's a lot of information that you have to provide to describe the preferences fully. If you make the additivity assumption, you just need k numbers, and that fully captures the preferences. So it helps you give a succinct description of people's preferences. It also helps you elicit those preferences efficiently, but on the other side is also a bit restrictive. Okay, so this sort of a trade-off here. Anyway, we'll assume that for the next few minutes. All right.
There is a lot of work on.
There's a lot of work. So people like the additivity assumption, they don't mind it in general, and there's a lot of literature on additive allocations.
And beyond.
And also beyond, yes. All right, cool. So what is a good allocation, right? What does fairness mean? I've spoken about fairness, but what is it? So one way of thinking about fairness is to look at how agents look at their own bundles and how they compare it with what someone else is getting. Right? Say I'm one of the agents, right? And if I'm getting something and I really like what someone else is getting, then I may not be so happy. I might complain to you that this is not a good allocation. So it helps to think about a notion called envy freeness, which says that every agent prefers its own bundle, at least weakly prefers its own bundle, compared to the bundle of any other agent. Okay, it does not want to have the bundle of someone else compared to what it has already got. So as an example, suppose we have these 2 agents and 3 goods, and the allocation that we are given currently is A is given to the red agent and blue gets B and C. Okay. So if you look at the red agent, its value for its own bundle is 4, just gets 1 item. And its value for what blue agent is getting is 1 plus 2. So I'm using additivity here. So red values its bundle at a higher number than the other agent's bundle, so it does not envy the other agent. Likewise, if you look at the blue agent, it values its own bundle at 1 plus 5 or 6, and it values red agent's bundle at 1, so it also does not want red agent's bundle, it's happy with what it got. So neither of the 2 agents envy the other, and that's why it's an envy-free allocation. A little bit more formally, so I'll denote an allocation, this object here, as this vector A, which consists of the bundles A1, A2 up to AN of the N agents. So AI is what agent I is getting, a set of goods that it is getting. I call this allocation envy-free if for any pair of agents I and K, you look at agent I's value for its own bundle and compare that with agent I's value for K's bundle, and agent I should weakly prefer its own bundle over that of agent K. Okay. And the important thing is that this is a pairwise property, so it should hold for every pair of agents I and K. No one should prefer someone else's bundle. Any questions about envy-freeness?
Envy-freeness gives some guarantee on like the overall utility of the system.
Yeah. So it does. I mean, in some sense, you are getting. So suppose my value for the entire set of goods is 100, right? And there are n people. I'm getting at least 1/nth of that 100. So at least some weak guarantees you can derive, but different envy-free allocations can have vastly different welfares as well. So,
I mean, or like additive function, can you say something stronger? Or?
It's something like price of fairness.
Yeah.
Square root n.
Or additive.
In fact, additive. Square root n.
Yeah, so the price of fairness concept is looking at the welfare degradation that happens if you impose some fairness constraints, and there's a lot of work including Siddharth as well. It looks at sort of bounds. Sorry?
Number of agents.
Oh, n, yeah, n is the number of agents, yeah. So in this picture, n is 2. In general, you can have n agents.
There's some notion. Here you have a fixed partition into say 2 bundles. Different partition might also be again envy-free, but
Absolutely. This is just an allocation which happens to be envy-free. Right? There are many ways to divide these 3 goods among these 2 agents. Other allocations may not be envy-free. In particular, if I give everything to red agent, blue agent will not be happy.
is the valuation for all possible envy-free partitions.
So that is really there. There always exists or close to it.
Yes.
Yeah. EF1, which is going to attain square root n fraction of the best possible. I mean, the gap can be quite large. You can imagine that one agent values everything at 10 million. If everyone is value everything at 0.1. Balance is a square, but yeah, square root n is the. It's not obvious why square root n.
All the items are like nothing is
Yeah, you can't leave anything on the table. Yeah, if you are allowed to leave stuff on the table, then it's very easy to be NV free. You don't allocate anything. Okay? If you really want to use up everything. All right, cool. So I hope NV fairness sounds like a natural and very desirable and compelling fairness notion, and at least I think so. But there are certain downsides to NV fairness. First of all, an NV free allocation is not guaranteed to always exist. You can think of very simple situations where let's have two agents and one item. Okay. Now, whoever does not get that item is going to envy the other person. So no matter how you allocate this item, you can't avoid envy. So there are simple situations where this very nice property may not be guaranteed. Oh no, let's not get there. Right? Okay, so existence-wise, this is not such a good property. Unfortunately, also computation-wise, it is not a great property because given an input instance, so by an instance I mean a matrix of this form, bunch of agents, bunch of items and their values, checking whether there exists some NV-free allocation, that amounts to an NP-complete problem. Okay, so deciding existence of fair solutions, fair in this sense, is hard. It's a very natural property, but existence-wise and computation-wise, not so nice. All right. So when you see such negative results, the Pavlovian response is to think of approximations. Okay, and sure enough, people have thought about it. And one approximation that I'll talk about in this talk is called NV freeness up to one good. It is a way of thinking about approximate NV freeness. What does it mean? So let's look at an example. Let's look at this red agent. So in this case, we are giving items C to red and A and B to blue. Now red's value for its bundle is 2, and its value for blue's bundle is 5, 4 plus 1. So there's definitely NV from red to blue. Right? But this NV is in some sense bounded because if you do a thought experiment, right, thinking that, oh, what if the blue agent did not get this item A? Then I, as the red agent, would not envy the rest of blue's bundle. So my envy towards blue is basically happening due to this additional item that blue is getting. It's bounded by the removal of this item. Okay. Similarly, if you are the blue agent, you can tell yourself this story that, look, my value for my bundle is 2, I envy red, that's fine. But if I remove one of red's items, then I don't envy the rest of red's bundle. So my envy towards red is also bounded in this sense. So in general, we call such an allocation A to be EF1 and we free up to the removal of one good. If for every pair of agents, I and K, there exists a good in K's bundle such that if you drop that good, agent I weakly prefers its own bundle over the rest of K's bundle. This is the sense in which the allocation is approximate and we free up to the removal of some good. And note that we are not actually throwing away anything. This is just a thought experiment. It's a hypothetical. We're just imagining that, oh, what if this item wasn't present? Is the definition of EF1 with everyone? Questions? Okay. Now the good thing with EF1 is that it addresses the two weaknesses of NV freeness that we saw in the last slide. So it remedies both the existential and computational complaints that we have. Okay. EF1 allocations are guaranteed to exist. So no matter what kind of input you give me, there always exists some allocation which is EF1. And not only that, you can actually find an EF1 allocation using very simple polynomial time algorithms. In fact, there is more than one algorithm that does that. So let me try to give you one algorithm which finds an EF1 allocation. It's a very natural algorithm that I'm sure many of us would have used in some other context previously. It's called the round robin algorithm. The way this algorithm works is that it gives names to the agents, say A1, A2 up to AN. Okay, it orders them in some way. And now it asks the agents to pick one item each, right? Their favorite item from whatever is left in this order. Okay. So first you invite A1, agent A1, you allow it to pick whatever item it likes. Okay. Then it goes at the end of the queue, then you ask A2 to pick its favorite item from whatever is left, then invite A3 and so on. Once you have run through the agents up to AN, you again restart from A1, A2 and so on. Okay. So you just continue this cyclical iteration until the items are used up. I'm happy with the problem. Fairly simple algorithm. All right. So what you can show is that the round robin algorithm, the allocation that you get by running this algorithm is actually EF1. It is approximately NV-free in the sense that we just described. Okay. Let me try to give you a sketch of how to prove this, because some of these ideas will actually become important later in the talk. So here's how we can prove that the round robin allocation is EF1. Remember, EF1 was a pairwise property. You have to prove it for every pair of agents. Let's pick some pair of agents, red and blue. Okay, and let's analyze the NV of red towards blue. Now there are two cases. Either red is ahead of blue in the round robin ordering, or it is behind blue. We'll analyze both of those cases. So if red is ahead of blue, then you can imagine the execution of round robin as follows. In the first round, red would pick some item, right, from its favorite from whatever is left at that point. Right? And later, blue would pick some item. Then in second round, again, red, blue, red, blue. Maybe in the last round, it so happens that there weren't enough items for both agents to get something. So maybe red gets something, blue doesn't, depending on number of items. All right. Now, the thing to observe here is that in the first round, when it is red's turn to pick something, both items, the one that it picked in the first round and one that blue picked in the first round, they're both on the table, right? But it chose to pick this item, meaning it at least weakly prefers this item over what blue picked in the second round. Right? Same argument you can apply to the second round, because again, this and this item both were on the table, but red picked this. So again, red weakly prefers this item over that. So item for item, red likes its bundle over blue's bundle. And maybe in the last round, blue didn't get anything, again, so red prefers this item over the empty item that blue got. Now, by using additivity, we can infer, we can transfer this item for item preference into a preference across bundles. Because you're additive, your value for the entire bundle is going to be at least as much as blue's bundle. Okay. So that means red does not envy blue. So if under round robin algorithm, if you are one of the agents, you never envy anyone behind you, because you always get to pick before them. So fairly intuitive. Let's look at the other more interesting case where you are the red agent, but you are behind the blue agent. Okay. So anyone wants to venture a guess? Or we can argue F1 here. Yeah. Exactly. So you compare the item that red picked in the first round with what blue picks in the second round. Right. So at this point here, both items are available, but red picked this item. So again, the item for item preference would look like this sort of diagonal arrows, right? So if you, for the moment, overlook the first item that blue picks, then again, item for item, red likes its bundle weakly better than blue's bundle. Okay. So once again, by additivity, if we forget about this item G, then red prefers its bundle over the residual bundle of blue. Any questions about this argument? This is why it's EF1. It's NV-free up to the removal of this item here. All right. So round robin gives you EF1. Very simple, nice polytime algorithm. That's all good. Okay. But there are situations where EF1 is not enough. Okay. Sometimes we are not satisfied with just some kind of approximate NV-freeness. And I'll give you an example where that might be the case. So let's think of a scenario where you just have these two agents, red and blue, okay? And say there are these two kids, okay? And on day one, 3 candies arrive, distribution between these two kids. Now we have just learned the round robin algorithm, so you very happily apply that, right? And let's say red is ahead in the ordering, So red gets 2 candies, blue gets 1. This is EF1, well and good. Okay. Now again on day 2, some resources arrive. You again apply the same round robin algorithm. Okay. Again, it's EF1. And red gets 2, blue gets 1. But I hope you see where this is going, right? Now again, you do the same thing on day 3, day 4, on and on. Okay. So sure enough, you are fair or approximately fair on a day-to-day basis. Right? But because you are using these deterministic algorithms, you are creating a systematic bias towards certain agents, especially if you sort of mindlessly apply this in a repeated allocation set. So that's a problem. So even though on a day-to-day basis you are approximately fair, the unfairness can sort of build up over time. The unfairness, the envy can build up. Okay. So it does not seem fair across the board. So one way to remedy this problem could be to think of randomness. Let's sort of toss a coin. Right? Hopefully that is going to be fair compared to what we just saw. So you might think, okay, instead of using the same ordering of agents every day, right? Let me sort of randomize over these orderings. Let me take a uniform distribution over all permutations of the agents, right? And pick something from the uniform distribution every time. Okay, that sounds fair, right? What could be fairer? You are choosing every ordering with equal probability. There cannot be anything fairer, right? Intuitively. Turns out there's a problem even with that. Okay, so even this very fair-looking idea can actually turn out to be unfair in some sense. So let me give you an example of how that can be. How this, like, why is it so counterintuitive? Okay, so the example is very simple. Okay, there's just 3 agents and 3 items, and these are their values for the items. Okay. Let's look at all permutations or all orderings of the agents. There's 3 agents, so there's 3 factorial orderings. Okay, let's put equal probability mass on all of these. Okay, so I'll select everything with 1/6 probability. Now, what I've written here is the items that agents would get if you execute that ordering. Okay, so I don't know. Let's look at this. So if blue agent goes first, blue's favorite is item A, so blue's getting A. Now, having given out A, if green goes next, it has to pick between B and C. So between B and C, it would pick D, and so on. Okay, so these are just the allocations you would get once you execute those corresponding orderings. So what we have now is a uniform distribution over these allocations. So I've written succinctly all this information in the matrix above. So the numbers here denote the probability with which each agent gets an item across all these 6 things, or the aggregate probability. Is it clear what's going on? All right. So let me set that aside. Okay. Let me bring back the preferences. So on the left, you have the values. On the right, you have the fractions of the probability. Now let's look at how agents evaluate each other's bundles. Okay, let's try to evaluate if there's envy in the system. Let's look at the point of view of the red agent. Okay, so red's preferences are given by this top row here. Now the red agent is comparing its own random bundle with the random bundle of the green agent. It's comparing 2 distributions, the one of its own and the one that green agent gets. And let's look at its value under both of those distributions. So for red agent, the value of its own bundle, its expected value, would be these values scaled by these probabilities. Yeah. And if you just stare at it for a second, it comes out to be 4.5. So the expected value of red agent under the uniform distribution is 4.5. And the expected value of red agent for green's bundle, surprisingly, turns out to be more than 4.5. It turns out to be 5. Okay. Anyone see a problem here? yeah, there seems to be some envy, right? If I'm ready, my expected value for green is higher than my expected value for my own stuff. So in expectation, I'm envious of green. Seems weird, right? We chose a very fair looking, very equitable looking algorithm, and still somehow fairness popped out from somewhere.
This is with respect to EF1.
Yeah. So we'll come to EF. So round robin, any execution of round robin is EF1, but this is a different kind of unfairness. And it's unfairness in the expected value sense. You're absolutely right. This is not the same as EF1. But anywho, even under this uniform distribution, there seems to be some envy in expectation. So that sort of forces us to think more systematically about what does it mean for a randomized allocation to be fair. By a randomized allocation, I mean an object of this form, which is just a distribution over deterministic allocation. For example, suppose with probability 0.25, I select this allocation, and probability 0.75, I select that allocation. This is an example of a randomized allocation. Or the uniform allocation that we saw in the last example. That's also a randomized allocation. So what does it mean for a randomized allocation to be fair? Right? We saw two notions for deterministic allocations, exact in between and EF1. What are similar fairness notions for randomized? So one notion you could think of is the one that was violated just a second ago. Right? That if you have a randomized allocation, no one should envy another person in expectation. There should be no expected envy. That's maybe one very natural property to write down. We are going to call it the ex-ante fairness notion. Why ex-ante? Ex-ante means before the coins are tossed, meaning stuff that is happening in expectation sense. So you have not tossed the coins and looked at a realization. You are thinking of before the coins are tossed. This is somehow economists like to speak in Latin, so they give these fancy names to fairness properties. Okay, so this is a desirable fairness property, ex-ante fairness. No one should envy another one in expectation. As we saw before, the uniform round robin idea does not satisfy this ex-ante fairness property. Right? But that does not mean it cannot be satisfied. In fact, there is a very simple idea which does satisfy it, which is to bundle everything up together, right? And if there are three people, you give that entire bundle with probably 1/3 to everyone. Everyone's distribution is the same. There cannot be any expected envy. Right? But is that fair? So if I bundle everything up together, and 33% of the time give stuff to Siddharth, 30% of the time give it to Anand, and 30% I keep it with me, does that sound like a fair deal? Or is there a problem?
3% yes.
Any thoughts?
Realizations are very easy.
Realization very skewed, right? Only one person is getting the entire resources in any fixed realization, while the other two are left empty-handed. So it does not seem very fair, especially after the coins are tossed. Right? So in addition to having no expected envy,
Would you even call it ex-ante fairness?
because this fairness is happening at the level of expectation. You have not realized, you have not tossed the coins yet. You haven't actually allocated the item, just looking at the distributional level. That contrasts with something called ex post, where you have tossed the coins, you have arrived at some deterministic object in the support of the randomized allocation, and now you're looking at whether that realization is itself fair or not. For example, in this bundle everything up strategy, it was ex-ante fair because the distributions were the same, no expected envy. But once you toss the coins and actually give the bundle to one person or the other, that's very unfair. So it was ex-ante fair, but ex post highly as unfair as it can be. So in addition to ex-ante, what you would like is some kind of ex post fairness guarantee. And because we have just seen EF1, let's ask that every deterministic allocation that is realized once the coins are tossed, is approximately envy-free, is EF1. Okay. So that's going to be our question of interest. we would like to find a randomized allocation of these indivisible items, which has both of these properties. It's NV-free expectation and approximately NV-free exposed. It's a distribution that is supported only over EF1 allocations. And there's no expected in. Is the question clear? Questions about the question? So this is what we are going to call the best of both worlds problem, because you're asking for two kinds of fairness, right? In the ex-ante world and the exposed world. So you want fairness in both worlds. So turns out that you can actually give a positive answer to this question. So for additive valuations, there always exists a randomized allocation, meaning a distribution over deterministic allocations, which has both of these fairness properties. Right? It is NV-free in expectation, and every realization is going to be EF1. And in fact, not only such a randomized allocation always exists, you can actually give an algorithm to find this distribution, this randomized allocation. So you can get best of both worlds in polytype. So I'm going to try to give you a rough sketch of this idea. And I realize this is a post-lunch talk, but I'm still going to talk about eating, so please forgive me for that. But okay, so the proof is going to be by an algorithm that uses eating in some way. As you can see, let me define what this eating idea is. The formal name of this idea is probabilistic serial procedure. It appears in the work of Bogomolin and Ghulam from 2001. They weren't thinking about this best of both worlds property. They gave this algorithm in the context of a slightly different problem. But turns out that the algorithm that they gave is very useful for us to answer the best of both worlds question. Okay. I'm just going to refer to this as the eating algorithm. All right. How does it work? So suppose you have two agents, and I've purposely drawn them as Pac-Man because they're going to eat stuff. Okay. Let's say you have these resources, the candies of different color, and these numbers denote the values that these agents have for these resources. So this is a usual valuation matrix. All right. Now imagine a time scale, okay, going from 0 units of time to, let's say, 2 units of, say 2 seconds, okay? And I've divided it into intervals of 0.5 seconds. Why am I doing that? Well, because in just a moment, I'll let these agents eat stuff, and I'll keep track of how much they have eaten at different points of time. So the way this algorithm works is every agent starts eating its favorite available item. So for, in this case, both agents like the yellow candy the most, so they both start to munch on it. We ask that they eat this stuff at equal speeds. Okay, so let's say they eat at the rate of 1 item per second. It's the same speed for both. So because they are both eating this at equal speeds, so after half a second, they would have both consumed the yellow candy completely. Right? Now, so the yellow candy is gone. Okay. Now, again, they're asking themselves, okay, what to eat next? Right. So again, they're going to eat their favorite remaining item at equal speeds. So for this agent, the favorite is the purple candy. For this agent, the favorite is the red candy. So now they can sort of eat in an uncontested manner. They can sort of have the whole candy to themselves. So starting at t equals half and until t equals 1.5, the two agents will eat completely the two different candies. Okay. Is the execution the algorithm clear? And in the last half a second, again, they're both converged to the green candy and they'll eat half and half of that. Okay. So once you finish running this algorithm, you get an allocation like this. Right? Every agent has maybe some full eaten candies, some partially eaten candies, and so on. One simplifying assumption that I'll make in this analysis is that the number of items is an integer multiple of the number of agents. So that just helps me keep the time scale ending at an integer value. If they are not an integer multiple to begin with, I can just add some dummy items which are of value 0 and sort of pad the instance that way. We'll just sort of make this assumption for convenience.
This won't even if not identical.
Yeah, items are not identical here also. So, for example, this candy has different values. Yeah, you can call them anything. I mean, I've just called them candies, but these are just any items. So this could have been an inheritance division problem, right? These are two siblings, and this may have been a house, this may be a car, this may be a painting. So I've just explained it in the form of candies. They don't have to be candies, but you can. So eating means just stuff. It's a hypothetical, right? It's a fractional consumption of. You're not actually devouring the house. Okay, all right. I hope the algorithm is clear with you. Okay, all right. Excellent. Okay, so what? So remember, what we are getting from this algorithm is an object like this. Okay? Now I'm going to represent this object in a more systematic manner. So what I'm going to do now is, as before, I have these 4 resources, but here you see more Pac-Man than before. Okay. What I've done is I've created a copy of every agent for every 1 second window. Okay, so this circle here denotes the copy, the representative of the red agent for t equals to 0 to t equals to 1. This window here. Okay. Similarly, this copy, the second copy, denotes the representative for the second window here, and so on. So I do this for all 1 second windows and all agents. Now, why am I doing that? Well, I'm doing that because I want to succinctly capture this information about what has been eaten by everyone during every time window. Okay. So because this was the representative for this first window, I'll write a 0.5 for yellow and 0.5 for purple here to denote what that agent ate in that window. Likewise for the gray agent. Similarly, for the second set of copies, again, I'll capture what that agent ate in that window. So in the second window, the red agent ate half of purple and half of green. So I put half and half here and 0, 0. So why did I do all this exercise? It is because I wanted to express the execution of this eating algorithm in a nice way where I can apply some nice theorems. Exactly. So as Siddharth is noticing, this is a very structured matrix here. It's a doubly stochastic matrix, which is to say that every row and every column of this matrix adds up to 1. Why would it always be doubly stochastic? Well, that's not too hard to see. For every object, i.e. a column, we have 1 unit of that, right? And we know that it gets fully consumed at the end. So the entries here must add up to 1 in every column. And every row should also add up to 1. Why? Because people are eating at the stuff of 1 item per time window. Right? So whatever fractions they eat overall across all goods, they must add up to 1. That's by our equal speeds assumption.
So can we get directly by solving an NP?
We can. Yeah, we can. Okay, so what you're getting at the end of this eating procedure is a doubly stochastic matrix. Now, whenever you see a doubly stochastic matrix in life, you should always think of the Birkhoff von Neumann theorem. Okay, what does it say? It says that any doubly stochastic matrix can be expressed as a convex combination of special kinds of doubly stochastic matrices called permutation matrices. Okay, a permutation matrix is a doubly stochastic matrix, but the entries are either 0 or 1. So again, all rows are 1, all columns are 1, but every entry is either 0 or 1. Meaning every row has exactly 1, 1, every column has exactly 1, 1. And convex combination means that you can sort of take 10% of this matrix, 50% of that matrix, 40% of that other matrix, and construct your fraction matrix there. All right. So by applying doubly stochastic, by applying Birkhoff von Neumann to our doubly stochastic matrix here, what we get is a decomposition like this. So with coefficient half, or I'm going to call these probabilities, with probability 50%, we get this permutation matrix, and with the rest of the probability, we get this permutation. And again, I'm not covering this, but you can actually construct this decomposition in polynomial time. Okay, that's not too hard to see. All right. So what does this all have to do with the best of both worlds fairness that we were originally interested in? Well, here's what. So this stuff here, you can interpret that as a randomized allocation. Right? People are consuming probabilities. You can think of fractions as probabilities. So this is like a distribution that you have constructed over these objects, right? Now, these objects here, you can think of them as legitimate allocations. Why? Because every item, you can imagine assigning it to the agent who has a 1 for that item. Every item has exactly one owner. You can infer an allocation out of these matrices, each of these. And what you have constructed is a probability distribution over deterministic allocations. So this is a legitimate randomized allocation. Now, I need to tell you why this randomized allocation is nice, in the sense that why does it have ex-ante fairness and ex-post fairness properties? Okay. So the reason this randomized allocation is yes. Yes. No, so you can actually show that they are sort of bounded by n squared if the n is the number of rows. By characteristic degrees, you get existence, but the bound is not too hard. Really, the idea is that you sort of you look at, you sort of imagine peeling off these matrices one by one, right? And the moment where you cannot peel off further, you take that out, and then the residual matrix is also sort of doubly stochastic and sort of. So not too hard to see. If you sort of think about it for a few minutes, you'll get. So you encode ex-ante NB-freeness in the usual way.
The expected value, right? We have a variable for each edge.
Yeah.
Allocated.
We just write X for this.
Xij for
Xijs, yeah.
for this
Yeah.
Ij, thank you.
But how do you ensure that like this?
You write the expected value for any bundle.
Right, sure. But how do you ensure that this speaks in the right order? I mean, you can execute the eating algorithm efficiently.
Right.
Kind of see that.
Right.
And you can like write an LP for only ex-ante fairness. But what is the LP for ex-ante fairness such that it satisfies this right eating?
So this is one of the solutions that LP might give you.
Yes.
But there could be other solutions as
Yeah,
well.
but also, but how do I zoom in on this? If I want to do it by hand.
Okay, I see. So I believe.
Stochastic.
My question was, yeah, you could just encode all this like stuff. Expected NB-freeness as an LP.
That is very straightforward. How do you sharpen this LP to exactly recover this?
Why do we?
It's just a different algorithm for the same problem.
I'm still curious to see how you that the support is here.
We'll get to that in a second. Yeah. Let me think about that question. I don't have off the top of my head. I don't have. You can do it for binary valuations, but I don't know the answer for general valuation. Let me think about it, and I'll come back to that.
So sometimes it is like again the LP helps.
Yes. Absolutely. Okay, so what we have so far is a distribution over.
Yeah, that's what. Yeah, sorry. Please go ahead.
Okay, yeah. So what we have is a distribution over these deterministic allocations, and we want to show ex-ante and ex-post fairness for that. Ex-ante is fairly straightforward to see. Why? Because if you think about the eating algorithm, every person was eating the best thing for themselves at any point of time, by definition of the algorithm, right? So that's why I like my distribution at least as much as whatever distribution you get. Because at every point of time I'm eating what I like compared to what you are eating. So that's sort of a hand-wavy explanation, but that's really sort of the observation here that that drives the ex-ante NB-freeness property. Okay. All right. So you get you get part of best of both worlds guarantee. Okay, I still need to tell you why you are exposed fair. Okay, so to show that you have exposed fairness, I need to prove that every individual allocation in the support is EF1. Yeah. Okay. So let's focus on just one of the allocations. The argument would be similar. Yes. Yeah. So that would hold in this case. Yeah, because I have padded the instance in an integral way. So that might include some dummy items. That's okay. But subject to the padding, everyone has equals. Yeah. Cool.
So what do you do? The number of items is more than.
I just add enough dummy things to make. Sorry.
The number of items is smaller than the number of agents.
I add enough dummy zero value items to make it an integer multiple.
Larger than one.
Again, I add enough to make it an integer multiple. It just has to be an integer multiple. Yeah. And that does not affect the analysis in any way. So. Okay.
I guess that only makes EF1 stronger. Not anything.
Yeah. So you don't have to remove the zero valued stuff if there's non-zero valued stuff in the other one. Okay. So let me focus on any fixed allocation in the support, and the argument you'll see sort of generalizes to all allocations. Okay. So remember, any permutation matrix was giving us an deterministic allocation, right? Every item is going to the agent who has a 1 in front of it. Now I want to claim it's EF1. Why? Well, the argument is very similar to why round robin was EF1. Right? There you can construct an item for item correspondence. How do you do that? The key observation to make here is that you look at any round T. So round means like, so this is round 1, this is round 2, that the time window. Okay. Look at any of those time windows. Any agent, say the red agent, is going to prefer the good that is assigned to it in the Tth round by this allocation here, compared to the one that any other agent gets in the next, in the T plus 1th time window. Why is that? Well, let's see. So I'm going to give proof by example now. So here's the red agent. Okay, let's say T is equal to 1. So it's getting the purple good. Okay, I am claiming that red likes purple more than what the other agent gets in T plus 1, which is the red good. Okay, red likes purple good over red good. Why? Because the reason that the second agent had a 1 here means that at least some amount of it was left in the second time window. Because there's a 50% mass on this, so there's at least non-zero fraction of it left in the second time window, meaning that good was still on the table. But the red agent still nibbled at the good that it got in time t. So it must weakly prefer that. So again, just based on this observation, you can construct this item for item correspondence. And this is the reason why, up to the removal of what anyone else gets in the first time window, you prefer your bundle over the bundle of anyone else, again by additivity. So this is the reason why you also get exposed here. Any questions so far?
Start with the LP, then this argument.
I'll have to encode. Start with the LP. I'll have to consider the decomposition carefully. If I don't do that, then of course all bets are off. Right? So it's all about how you decompose your LP solution over integral ones.
The LP, like if you do not like you just write an LP only for ex-ante fairness, it can give you solutions that cannot be.
Absolutely.
In particular, like
I'm not claiming that every fractional EF allocation can be decomposed. I'm saying this very special kind of allocation you get from eating can be decomposed. Yeah.
Just have a variable for every sort of quanta of time. Like import this stochastic dominance. Pick an agent, look at the probability mass on all goods above this.
Yes.
That has to be at least for the stochastic dominance kind of a thing.
So you get an SD NV free fractional allocation.
Yeah, which is what.
Yeah, which is what this is. Yes, exactly.
SD. stochastically dominant can be written as an NP. That's my
Yes.
the way you like the way it's done here is just to sort of mimic the tiny thing. Sort of.
That's right. Yeah. I'll have to think about why the STNV free solution would be as easily decomposable, but yeah, let me think about it. It's not completely clear to me. Let me come back to it maybe once I'm done with the slides. Okay. Okay. So this was the proof why for additive valuations we can get both ex-ante and ex-post pairs. Okay, and you can I didn't argue this formally, but you can execute the eating algorithm and the Birkhoff decompositions both in polynomial.
Also gives you EF support on EF1 allocations that are balanced.
Yes. Yes. So yeah, by balanced, Siddharth is referring to an allocation where everyone gets the same number of items or almost same number of items, because I said you can add some dummy goods. So even the dummy goods are kind of equally distributed. So once you take them out, the original goods are also within one of each other. So, all right. Cool. So the main result that we discussed is that ex-ante EF and ex-post EF1 are achievable in polynomial time when you have additive valuations over goods. Okay. I want to just highlight some open questions, some extensions of this result, which are of definitely a lot of interest to me, and I hope you'll also find those questions interesting. The first extension that one might think of here is for the class of valuations. So the result I presented was for additive valuations, but valuations don't have to be additive, right? What about other classes of valuations? So often sort of the picture that people think about is that, okay, you have this class of additive, right, but it's sort of sitting inside some other valuation classes, say submodular valuations or more generally monotone valuations. Okay. Submodular is a bit more technical to describe, but monotone just means that you like set-wise bigger bundles compared to the smaller ones. You feel like more stuff. Okay. What we know, even for this biggest class of valuations, monotone, is that an EF1 allocation always exists. In fact, you can also find such an allocation using polynomial number of queries, valuation queries. Okay. So even for the biggest class, we have ex-post EF1. Right. What we do not know is whether, this EF1 can be combined with ex-ante EF. We don't know how to construct a distribution over EF1 allocation, which is an NV-free expectation. So that's an interesting question to think about, right? We have some understanding of this class here, but what happens for submodular or subadditive or monotone and so on?
Did you give like query access to?
You're given, yeah, I give you a bundle, you tell me its value.
So we don't do like LTR.
That would be harder. Yeah.
Even for explicit submodular.
Yeah. So there's some recent results which say that for subadditive, so subadditive is something that is between submodular and monotone. Okay, you can get ex-post EF1 along with not ex-ante EF, but some approximation of EF, like half EF. Half EF means that my expected value is at least half of my value for your bundle. So sort of slash the benchmark a little bit. But can you get exact ex-ante EF with ex-post EF1? We don't know. And that's open for pretty much beyond additive. Yes. So the second extension that Siddharth is hinting at is, instead of, okay, let's keep the valuations to be additive for now, but let's try to strengthen the ex-post fairness guarantee. Okay, we're not happy with even EF1 now. We want something stronger. So one property that has sort of gotten a lot of attention is called NV fairness up to any good, or EFX. So in EF1, if you remember, we said that there exists some good in the other person's bundle, which if you remove the NV goes away. So the quantifier was there exists. If you change the quantifier to for every, you get indifference up to any good EFX. Okay, so this guarantees a stronger guarantee of fairness, and it implies EF1. Okay. This is actually a surprisingly challenging property. We know not that much about this property. So we know that so EF1 always exists, right? Even for very general valuation classes, any number of agents. EFX, the best result we know of are that it exists for 3 agents. If you have up to 3 people, you can guarantee existence of EFX. But if you have 4 or more people, we don't know. We don't have a proof. We don't have a counterexample. It's one of the big open questions in the area to understand the existence of EFX allocations. So can you show ex-ante EF and ex-post EFX? That's an even harder question than that, because in addition to just ex-post EFX, I'm asking you to give some in-expectation guarantees as well. So this is again a very challenging problem. We have some partial results on this. So in some ongoing work, we have shown that if you ask for something stronger than ex-ante EF, something called ex-ante SDEF, stochastic dominance and freeness, not defining that, but a stronger ex-ante property is actually incompatible with ex-post EFX. Right? So if you strengthen both ex-ante and ex-post properties on the slide, you get a negative result. But what happens for this slightly weaker property of ex-ante EF and ex-post EFX, we don't know. Very nice question. So if you resolve this question positively, you'll be very famous. Okay. All right. Okay. Speaking of strengthening the ex-post guarantee, you might say, okay, I'm happy with EF1, right? But I also want to please economists. Okay? And one guarantee that economists like a lot is Pareto optimality, which informally says that there is no better way to reallocate the resources. Right? There is no obvious way to redistribute the resources so that the society won't object to that. The hand-wavy definition of Pareto optimality. Again, what we know is that if you just want EF1 along with Pareto optimality exposed, just that, then such allocations always exist, right? For additive valuations. You can show existence of EF1 and Pareto optimal allocations separately, just in the exposed sense. But what if you want exposed EF1 and PO, again, along with ex-ante EF? Again, we don't know. So this is, again, one of my favorite open questions in this line of work. And the final open question I want to talk about is, suppose the resources that you're working with, they are not goods, they are not desirable objects, but they are undesirable objects, things you don't want. So these are not items of inheritance. These are, say, household tasks. So who does cleaning of the dishes, who does gardening, who cleans the floor, and so on. Okay, so you have negative value for these items now. Once you have negative valued items, well, you can ask all of these questions again, right? Can you get ex-ante EF, ex-post EF1, EFX, and so on? For chores, just like for goods, we know that EF1, if you just want EF1, such allocations again exist even for monotone valuations, right? But again, if you can, whether you can combine EF1 along with ex-ante EF, we don't know. Again, nice problem.
For this particular style, like the proper adaptation, so you pick the least, you have X counterexample.
For chores, if you're just thinking of additive chores,
yeah,
you can again do this eating business, and you can again do this work of annulment, and you can actually get EF and EF1. But what happens for sort of beyond additive or stronger property combinations and so on? All of those questions that are open for goods, they're kind of mirror images are open for chores.
But this
question, if you just replace goods with chores, we know the answer. Yeah. All right, that's all I had to say. Thank you for your attention. I'm happy to take more questions.
Secretive.
Weighted?
Secretive.
Secretive. Okay. Okay. Yeah, there is some work, including by Siddharth, like suppose one of the agents is missing, can you still compute fair allocations without assuming anything about that person's preferences? So we have, I think, some results, but yeah, best of both worlds style results, I don't think I have seen in that context. Um, yeah.
Reported to fully.
Values.
Yeah, yeah. So you propose the algorithm, when they report their value truthfully. So then for some negative results. The truthful mechanisms are.
Yeah, so so truthful revelation of preferences. So throughout, I assume that this matrix was always given to us, right? And I assume that those are indeed the preferences of the agents. But what if people try to game the system? They don't give you the correct numbers. They have some other preferences in mind, but what they write on paper is different from that.
But this mechanism does.
Yeah, everything is EF1 with respect to what has been reported. It may or may not be EF1 with respect to the true things, the things you have in heart, right? So I assume that people report what's in their mind, but if that's not the case, then all of these bets are off, And like Siddharth is saying, there's a conflict between fairness and truthfulness. The results would say that if you want EF1, you cannot hope for truthfulness. There's a conflict, fundamental conflict between them. Very strong negative results. And again, if you impose ex-ante indifference on top of that, it's only going to get worse.
Binary calculations.
Binary additive, binary marginals. You mean? I don't know about general binary marginals. For binary additive, actually, you can do this LP style approach as well. So you can actually write LPs because there, when you write EF1, you know that the marginal is 1. You can sort of try to ensure that. So it's easier to write LPs, and you can actually decompose it using some nice techniques. For binary non-additive, so sure actually. Yeah, binary marginals for monotone violations. But in general, it would be nice to know if non-eating approaches can also give you similar results.
There's also this like complementary thread of work where what you do is you have subsidies.
Yes.
So you say you actually look at proper MVP-ness.
Yes.
But say that I will sort of now pay people. So
Yes.
in addition to a bundle AI, I'll give you some money.
Mhm.
So you will evaluate your bundle as AI plus
The payment.
AI. You evaluate some other guy's bundle as AI agent plus PJ.
Right.
So it's wondering if you can get some incentive. So the goal there is typically to show that you don't have to make too much pay. Like the PIs are small and still you're wonder if you can argue some thing like ex-ante you have very fairness and it's supported on bundles that require very low pay.
So you're wondering if I can.
So ex-ante I'll give you any fairness.
Maybe my payments are skewed. Maybe one agent is getting a lot of money, the other is not getting enough money.
Yeah.
You're thinking of looking at.
I'm saying, okay, I give you a distribution. So instead of being supported on EF1,
Right.
I'm now saying it's ex-ante MVP. So in expectation, it's MVP,
Yeah.
but it's supported on allocations that require very little.
Okay, I see. So you don't want to pay enough money to go all the way to exact infiniteness.
Yeah.
You're saying, okay, I'm happy with some kind of approximate infiniteness.
Yes.
But can I change around the payments?
Yes.
So that distributionally I'm
expected
in briefly. Okay, I see.
Yeah, maybe. So this is support kind of interest here, like I think those are two activities. So you said like you could have n square at worst or m square.
You can actually get linear. So it's m times n plus 1.
Okay.
Linear in the sense of the matrix size.
That's sort of again tight.
That is tightish. But you could ask a different problem. So can you construct randomized allocation with small support? Does the given instance have such a small support? I believe I've seen some papers asking this question in the context of Birkhoff for like general double stochastic properties. There are some hardness results actually.
Approximations you can get like dimension 3 result. MMS and proportional, are they looked at in the same sense?
There's some work on best of both worlds for MMS and so on. It was by Bayoff and some results are known, but again, whether you can, let's say, the 4/7 group wise MMS guarantees, can you combine them with ex-ante EF? Those kind of questions. So maximum share is oh, sorry. Okay. Yeah, MMS is a different guarantee than indifference. So it basically sort of gives it asks that every agent should be above a certain threshold satisfaction. The threshold is defined in a convoluted way, but that's. Okay. Thank you so much.
It's too loose.
Thank you. Thank you so much.